It took much longer before people realized that the planets are very close, are part of the same system, and revolve around the sun, whereas it was never suggested that the stars revolve around the sun. Imagine for a moment that the universe has just appeared in the state it is in today. You won't see? The first thing you'll see is the moon after 1 second, because light takes 1 second to arrive. You'll still have to wait 8 minutes before you can see the sun, for it to catch up. Between the sun and the first star, well, that's still 10,000, 40,000 billion kilometers.
History of the Universe with Daniel Kent. I took it.
Hello to the track, hello.
Go ahead and introduce yourself for those who don't know you yet.
Then go ahead. That's his name.
That's perfect.
At the Paris Observatory, at the Paris Institute.
Radio Canada there, you wrote a book some time ago called The Words of the Sky, yes? So what is this book about? What does it talk about?
Listen, there's something I discovered about 10 years after I started doing astronomy. It's that in our everyday vocabulary, the words of the sky, the ones we use in daily life, well, there is a kind of permeability. It's from having looked at the sky for millennia, so it's not really surprising that our vocabulary is completely peppered with it. Well, peppered isn't very nice, but influenced by the sky that surrounds us, so there are plenty of words we use without even knowing where they come from, actually. Because that's how I became interested in linguistics. I found it fascinating. It's a science that's obviously quite different from astronomy because words form families, change meaning, and sometimes disguise themselves. Sometimes it's very complicated to know where they come from. You even have words that are identical and have completely different meanings, like péché, péché, pêcheur. That doesn't mean the same thing at all, depending on the context. So I became interested in words related to the sky. And actually, as is often the case when you go looking for mushrooms in the forest, when you find one, you end up finding the others because your eye gets used to it. It knows how to find them. It understands the context. And I found about 100, maybe 200, maybe even more. Some are fascinating, others are less interesting, and others still. And well, that's it. And so I then thought about taking all of that and making a story out of it. By the way, in this book that I brought here, which is called Les mots du ciel, and well, that's something that I find very interesting.
And I saw some pretty incredible things. For example, the word consider, apparently, comes from the sky.
So, among the words of the sky that I have listed, some are indeed words that we have named, that the sky has directly inspired us. And we also have named the sky, we gave names to the constellations or presumed gods that are in space. And so there is a back and forth, sometimes we name, and sometimes the sky gives us words to name things. So, for example, one of the simplest words, indeed, you mentioned constellation. So constellation led to constellated simply because we started by observing constellations, the stars grouped together, and then we used the word to express something else. There you go, you are constellated with jewelry, there you go, that's the state of being constellated. When it comes to the role of the stars, it will indeed intrigue. Are the stars there to decorate, for us to pray to them, to invoke them, or on the contrary, do they influence our destiny? And that gave rise to a whole series of words like consider, be stunned, disaster, because the word star can be ominous, so it's a disaster. Yes, the Italian word is siderism, so that gave us consider siderism in the sense of sailors, meaning to look at a star, to observe it, cosa, so looking at a star means measuring its position at sea. There you go, that's how we got consider. And the opposite of what? Yes, I'm interrupting you. The opposite of consider is a privative term, it's decidera. And decidera means not looking at the star. And when we don't look at something we love, what happens? We feel a sense of regret, it leaves us, and we desire it. So decidera, an R and a D dropped out. It's not very pronounceable. And so from considera, we've arrived at desirer. So it's really a word from the heavens, maybe one of the most beautiful, since it speaks to our life force, to our most basic vital impulses. But then there are others, much simpler, that are maybe obvious, like tournesol, for example. It's a flower that, yes, a flower that turns with the sun. You can clearly see it turns with the sun and how it's made. Others are much more mysterious. For example, malotru. Malotru, today it means someone who is rather rude, ill-mannered, but malotru in the past, you have to realize that first. You have to remember that our ancestors used to look at the sky every day. Even before they established cities, towns, and villages, they were hunter-gatherers and looked at the sky. They always had the sky above their heads. So it inspired both fear, respect, and poetry. But the word malotru comes from the fact that in villages, when a child was born, well, people would immediately go outside and look up at the sky. And if there was a very bright star, it was a good sign. Signs that you were born under a lucky star. You see all those expressions. But on the other hand, people didn't really know. And sometimes the child was born rather frail, not very lively, and people would wonder about it. And then people would say he was born under a bad star, the malum astrum, the bad star, and that's where malotru comes from. And then the change in meaning happened around the 17th century under the influence of Voltaire, actually, who used the term to refer to someone who is rude, a rude person, if you will.
Okay. It's still quite fascinating because observing the sky is so deeply rooted in humanity that, as a result, it actually influences and reflects in many other aspects. Yes.
So there are terms that actually come from direct observation, like, for example, the dog days. Dog days comes from the Latin word canis, meaning dog. Does that seem clear to you? No, it's not. Obviously not. There is a star called Sirius, which was a fundamental star for the Egyptians, because when the Egyptians observed the heliacal rising of this star, heliacal rising means it rises before the sun, just before the sun. You have to imagine that the astronomers were constantly watching the sky. Well, it indicated the upcoming arrival of the Nile floods. And the Nile floods, for a river civilization organized around the Nile, were fundamental because it brought silt, it brought something that would then allow them to farm the fields and ensure the prosperity of the empire. And so it's extremely important. And the year began at the time of the heliacal rising of Sirius. So Sirius was called the Wanderer at the time. And then it was the Greeks who obviously observed this star, which is the brightest star in the sky that you may have seen, especially during winter nights, because it's a star that follows the constellation Orion. And for the Greeks, Orion is the hunter, he's a god. And he was, like any good hunter, followed by his dog Sirius, which is the most beautiful star. And you see how it worked. So we go from the Greeks, the Egyptians, who thought about the Greeks. We have Sirius, the hunter. And the Latins took up the term, since canis means dog, and canicule, so it's the periods of great heat that we inherited from the Egyptian tradition. So canicule still today actually refers to periods of great heat, and we find this term in other languages as well. You see, it's very interesting to see how words evolve. In Russian, they use the word canicule, which actually comes from the same origins. But there, it's used to refer to vacations, not great heat. People vacation when the weather is nice. That's it. All right, so there are plenty of other words. Obviously, jovial comes from Jupiter. There you go. You have Saturnism. It's lead poisoning. Why? Because lead is associated with Saturn. So finally, lead was named after Saturn, who was named by us as one of the gods, since the planets were associated with the gods. You see, so there are back and forths like that all the time.
But why did we make this association then between planets and deities at the time? Well,
imagine 2,000 or 3,000 years ago outside with the sky above your head. It's not so rare today. We hardly look at the sky. Back then, it wasn't like that. And the first thing that strikes you is this sky that's there that looks like a dome that's turning. There's a regularity, there's a kind of beauty that grabs you, really. At the same time, it can be unsettling. I invite you to try it. I invite you because it seems so simple that we don't do it anymore. But stay outside for half an hour on a summer day. Look at the sky. Wait until your eyes are well adjusted. You'll see many more stars than what is mentioned in the literature. You'll see 3,000, even more if your eye is sensitive enough. Well, you can clearly see that the sky seems to turn little by little. And the ancients noticed that. They saw that indeed there is a regular pattern. The constellations move one after another, coming back night after night. In the same way, there are still some small shifts. Because as the seasons go by, well, it's not the same constellations that appear. That's because the Earth revolves around the Sun, of course. That's what's reassuring. But superimposed on this kind of divine scenography in a way, you know. Well, they noticed that there were some phenomena that were quite strange. Some celestial bodies didn't behave like the others, which moved across the fixed stars. They're called fixed stars because their shape doesn't change. The Big Dipper is always the Big Dipper. Well, these celestial bodies were called wandering stars. They were the planets. Planets, that means, again, one of the words from the sky, it means wandering stars. And so, indeed, they spontaneously thought, well, that's strange. We need to find an explanation. Men and women, we have a hard time living without explanations. That's actually what makes us unique. Well, they called upon the gods, the deities. They thought behind this independence of mind, there's something hidden. And it's certainly connected to the idea that it's the gods who are watching us. And from the moment you have that feeling, you say, how are we going to communicate with the gods? And that's one of the foundations of astrology, which is to try to find, because the sky doesn't say much, it's very discreet, it doesn't say a lot, it's hard to decode, it took thousands of years. Well, astrologers aim to try to understand what hidden intentions were behind these movements of the planets. Sometimes the planets are close to each other, sometimes they disappear. So there was a whole planetary language that formed the foundation of astrology and was connected to the gods. And by the way, the origin of the gods, or rather the names of the planets, for example, Mars was a god, it was Nergal, the god of war for the Babylonians and the Messenians. And Venus was associated with the goddess of love. Jovial, that's Jupiter, because Jupiter is the god of gods, the one who is lively, who provides energy, and so on. There you go. All right.
So how did we move then from these projections, actually, these interpretations, to a slightly more precise understanding? Because at some point we understood that these celestial bodies that moved on their own were actually orbiting the sun, and that we too orbit the sun. How did we move from one to the other? Yes.
It still took some time, though. That's it. It didn't just happen spontaneously. For both religious and intuitive reasons, people thought that we are at the center. We always feel like we're at the center of something. Even when we're just walking down the street or in the desert, you're the center. If you turn all the way around, 360 degrees, you're at the center. So this position psychologically led us to think that we were at the center of the world. On top of that, the celestial vault gives the impression of solidity. The firmament, that's not by chance, it's not that. Even the farm also gets its name from that. It's a big solid beam, which is an analogy with the firmament. So it took a long time before people realized that the first representations of the solar system were like that. The Earth is at the center, the planets revolve around it. And it was quickly noticed that there were still some complications with that. People tried to understand the movement of the planets by assuming that the Earth is at the center. Well, that immediately led, especially with circular orbits, to complications, quite difficult to solve. And people tried to add small additional circles. Well, it's a Ptolemaic system, extremely complex, and it became more and more complicated over time in order to best reproduce the observations made with the naked eye, even with instruments. We didn't have many instruments. We had to wait for Galileo before we really had instruments that allowed us to make more precise measurements. So until that time, the Earth was at the center of the world. Then people realized that isn't possible, and Copernicus proposes another hypothesis, both to simplify the calculations and also because he thought, after all, why imagine the Earth at the center? Why not the Sun? So he brings a different model, and that's when, with Galileo starting to observe the world with an instrument, which is no longer the eye, but the telescope, that's when indeed he realizes that's when we really start to make the distinction between planets and stars, because before we didn't really know how to tell the difference between planets and stars, except that the planets were wandering objects while the stars were fixed. That was the only difference we knew. It took much longer before we realized that the planets are very close, are part of the same system, and revolve around the Sun, whereas it was never thought that the stars revolve around the Sun. The stars were other suns, other apparent suns, which was proven much later. We had to wait until the 1700s.
That's quite recent.
Yes, it's quite recent for the first measurement of the distance to a star, which is Proxima Centauri, to be made, and allows us to understand when we calculated the brightness, the actual luminosity of this star, it's Proxima Centauri. If you asked in a quiz, yes, I think so. Proxima Centauri, well, it's 4 light years away from us, which means it takes 4 years for light to travel from Earth to that star. 4 years, that means 40 trillion kilometers. That's not nothing after all. And there, this star is barely visible. It's not even visible to the naked eye. But this star, when we calculate, well, when we measure it, we measure its brightness. And given the distance, we realize that it shines as brightly as the sun. And so we understood that the sun is a star and that stars are suns, which is not the case for planets. Planets are much closer. They orbit around the sun. They're even like tiny specks of dust. It's negligible compared to what a star like the sun is.
Which means that, in fact, this understanding we have of the universe, of the space around us, is actually quite recent. When did we finally understand that our galaxy wasn't the only galaxy?
So yes, that's true, what you're saying. For a very long time, progress is kind of exponential. We start little by little. That's it. And then all of a sudden, when everything accumulates, because on one hand, it's even like the story with mushrooms, we find them, Then after that, we want to, and then more and more people get interested. We talk among ourselves. It's really something. There's a percolation of knowledge. So there you go. At first, it's isolated, and then meetings make it happen. And regarding the Milky Way, it has obviously been the subject of many explanations, myths, and various representations. Just the milk itself, right? Milky Way means the path of milk, and that comes from Greek mythology, which says that when Hercules suckled at his nurse's breast, well, Hera, actually, she wakes up, she sees what's happening, she pushes him away, and from Hera's breast bursts a stream of milk that spreads across the sky. It's very beautiful, certainly more true than what they tell you now. But, well, we still have to remain scientific, even in the presence of a non-scientific audience. So it's this idea that you have a ribbon from the East that comes from Greek mythology. Then afterwards we understand, thanks to Galileo's instruments, to Galileo's telescope, which was fundamental. It's an opening, it's a window to the world, this instrument. Maybe we'll come back to that idea. But here we see that in the Milky Way there are many things. There are star clusters, there aren't any planets, right? The planets, it's simply the 5 planets that we know, and little by little more became known, bringing the number to 6 or 7, all orbiting the sun. But when we look at the Milky Way, we see star clusters, we see dark areas, we see bright nebulae, and the question arises, we actually see a lot of bright nebulae, little clouds that are more or less significant, and we wonder about these little clouds. We call them nebulae. By the way, that's also an interesting term, because when we talk about it, if you ask someone, you say, is what you just said nebulous? It means it's a limit of our knowledge. It just marks our ignorance. It's nebulous. That is, we didn't really know what it was about. To such an extent, by the way, that there was an astronomer at the time named Messier who was a great comet hunter. Comets were also of interest. It's part of those objects that appeared from time to time, like the planets, right? The planets, there was regularity, yes. Whereas with comets, we had no idea when they would appear, hence fear, terror, superstition, and so on. So Messier, he hunted comets, well, peacefully with a telescope. And when he very often realized that what he thought was a comet was actually a nebula, because he always saw it in the same place, always in the same place, in the Milky Way. And so he made a catalog to set his colleagues straight. If you find this, be careful. Warning, it's not a comet, it's a nebula. He found 101 of them, that's it, with sometimes with shapes that are a bit strange, but they're always nebulae. And so we asked ourselves this question, what do these nebulae correspond to? And obviously during that time we build instruments that are more and more powerful, more and more advanced, which is what makes an instrument powerful. And that's what actually allows us to open up the sky, a new window onto the sky. It has long been astronomical telescopes. The first telescopes, well, the most beautiful telescopes. These are pieces of glass that could be 1 meter, 1 meter 50 in diameter. It's terrible to polish, you know, there were difficulties. Moreover, it's very difficult to curve the surface of the glass so that you have a short focal length. No, the focal lengths are very large. That's why if you go visit old telescopes, you can see them in the United States, even in France, a bit everywhere. You see very, very, very large telescopes. The lens at the entrance, the piece of glass that formed the entrance. The lens it can be 50 cm or 1 meter, but you have to go observe 20 meters farther. The focal lengths are very, very long. So we start doing that. We invent the telescope. Herschel, for example, in England and in France too, we make them, Foucault in particular. And there, obviously, observations become crucial because they allow us to make images. We invent photography, but before photography, we looked through the eyepiece and then made drawings. That's what Galileo did, by the way. Galileo's drawings are wonderful to look at. Very precise. He did it in the dark. When I started observing astronomy, I was in the dome. And I looked through the eyepiece to make sure the telescope kept tracking the celestial object I was interested in. And I observed in total darkness. And then I took photographic plates, but at the time, Herschel or Lord Rosse in England, well, they had a little magnifying glass, and then they looked, then they made a little sketch like this, and then they looked again, made another sketch. And sometimes the drawings are beautiful. I recommend you take a look, just go on the internet and type Lord Rosse, R-O-S-S, and you'll see the drawings he made, which are beautiful. Especially of galaxies called the hunting dogs, which you can compare the image we get now with photographic plates. It's absolutely extraordinary. So little by little, we end up drawing these nebulae, but the question remains whether these nebulae are part of the Milky Way or not. Well, yes, I'm taking a bit long to answer because there's the whole history of astronomy behind this. It gives substance to how we get there with our instruments. And there was a debate, the great debate between two astronomers, Chaplet and Curtis. Chaplet claims that no, all of this is part of the Milky Way, and Curtis says no, not at all. No, these are nebulae. You see, these are Milky Ways that are located much farther away. And the stakes here are tremendous for our way of inhabiting the world, because what does it mean
notre manière d'habiter le monde
if we stay in the Milky Way? We quickly understood that the Sun was part of the Milky Way. It was just one star among others. We understood pretty quickly that the Milky Way was a disk. Well, it was more or less clear, but it was our world. And then there were these nebulae, which looked like kinds of smoke, excess elements, I don't know how to explain it, or dead stars. But if, on the other hand, you imagine that there are also other Milky Ways, you have to place them at a certain distance. And so, as a result, the universe becomes vast. And you have to wait a long time. This debate is actually part of what fuels science, you know. Doubt, discussion, criticism, and little by little, well, there you go, you need observations. Unlike astrology, for example, where you just say that's how it is. If it doesn't work, there's always a reason. We always stick to the same basic principles. Here, we're ready to abandon our hypotheses. If it doesn't work, we give up. But we make observations to verify them. And who will verify? Well, that will be Hubble, this astronomer we haven't talked about yet, I think. Edwin Hubble, who had a boxing career, who did amateur boxing, who also had a career as a lawyer, but that didn't interest me much. He arrives in California around the 1920s, and he feels that things are happening in California. He has in particular a telescope that's 2.5 meters in size. When I say 2.5 meters, I'm talking about the mirror. A mirror with a diameter of 2.5 meters, which was already... You really didn't want to break that, you know. It's not 7 years of bad luck, it's an infinity of it. So he joined the group of observers at Mount Wilson. It was set up at Mount Wilson, which is a mountain that overlooks the city of Los Angeles. And he observes, and he's the first to make, well, he's not the first, but he makes extremely interesting photographic plates and what we call spectra. He makes spectra that allow him to show. So the spectrum is a way to analyze the composition of the light from a celestial body or a star. And well, we can, with this technique, measure the distance or know if the celestial body is approaching or moving away. So before him, there were already other astronomers, especially Silver, who had also observed that some nebulae seemed to be moving. Well, he does it systematically, but above all, what he does is take images, photographs that allow him to verify that a star changes intensity in this galaxy, or rather in this object. I didn't know if it was a galaxy at the time, but this star, which pulses regularly, is called a Cepheid, because the first one was observed in the constellation of Cepheus. A female astronomer, Henrietta Leavitt, noticed that when these stars pulse, there is a link between their pulsation and their brightness. That is, those that pulse very slowly are much brighter than those that, or the opposite, I'm not sure anymore. There you go. So there was a relationship between the pulsation and the brightness of the stars. And Hubble observes one of these nebulas whose distance is unknown, and he realizes that indeed there is one of these Cepheids there. That's very valuable. It's the first time a distant Cepheid of this type has been observed. He observes this variation in brightness and adopts the brightness distance criterion. He says, since I have the brightness, now I have the pulsation, I know the brightness, and I can calculate the distance, since I can see whether this star is faint or not, bright or not. And he actually realizes that this galaxy, this object, is a galaxy far away, well beyond the Milky Way. And at that point, it's truly revolutionary because we understand that the universe, as a result, is much vaster. And the next step is to observe many more of these stars and to realize that there is a connection, that these stars, these galaxies, seem to be moving away from us. And that's when they discover the expansion of the universe, which once again adds to this idea that we live in a universe much vaster than what we had understood until then.
All right. So, if the universe is expanding, what happens if we go back in time? So, can we reconstruct the history of the universe? Yes.
But that's exactly the beauty of the system. It's a bit like when you see a diver diving. Phew, you see that he fell like that. Nothing stops you from saying to yourself, hey, maybe if I rewind my film backwards, I might see where he came from. You might realize that he comes from a diving board and so on and so on. Well, and here we say to ourselves, since we live in an expanding universe, the Milky Way is not alone. There are other galaxies. By the way, we're discovering more and more of them, just like my story about mushrooms, and we're finding out that they have various shapes. Some are elliptical, others are spiral, others are irregular, but all of them have in common, except for a few that are very close to us, all of them have in common that they are moving away, and the farther they are from us, the faster they are moving away. There you go. This property is quite astonishing. That's what determines the structure of the universe and the fact that we can trace it back. And so we think if we go back in time, let's say 1 billion years ago, well, these galaxies that are moving away must have been closer to each other. There you go. Then after that, you have to do a bit of arithmetic. You learn a bit about how to calculate these speeds of separation. And that's when we come to models where we end up estimating the age of the universe, so that everything is actually at the same point, in quotation marks. We come back to the idea that Jean-Pierre was developing earlier. So there you go. There's a singular moment when everything has to end up stuck in the same place, with all the difficulties that this implies. We talked about the singularity, okay? And now we're continuing to try to understand, to get a little bit away from these demands of physics that we have to understand with the laws we have. And so this notion actually emerges directly from Hubble's observations in the 1920s. All right. And in fact, we do it by working backward. We're constantly rewinding the story. So what's interesting is that when you observe a group of galaxies that are, for example, a few million light years away from us, so that means the light took 1 million years, or 2 million, or 3 million, or 10 billion, 5 billion years. Well, it's like turning the pages of a book, if you will. We read the first pages. The first pages are the closest objects, the stars that are nearest to us. Those are the stars. So, for example, Alpha Centauri is 4 light years away. And then, as the stars are farther away, well, you have to turn the page. You have to wait for the light to arrive. You can imagine for a moment that the universe appears just now as it appears today. You won't see it. The first thing you'll see is the moon after 1 second, because light takes 1 second to arrive. You'll still have to wait 8 minutes before you can see the sun, before daylight can appear. All right. Then you'll have to wait 4 years before you see the first star. So in the evening, you won't see anything because, well, your universe is too young for you to see stars in the sky. But after 4 years, you'll see a star, Proxima Centauri. And then, as the years go by, well, you'll see more and more stars. So now, obviously, the universe is so old compared to us that everyone is there, you know. We see all the stars. We see all the stars in the Milky Way. We even see other galaxies. And then with instruments, we can see as far back as 13.8 billion years. And but then you might say that's the end. Well, yes, that's the end. It's the end of our universe. We're in a bubble. What we call the observable universe. If the universe is really 13.8 billion years old, what does that mean? It means that light took 13.8 billion years to reach us. So that means that a star, if there is one, and we do think there is, obviously, that would be located at a much greater distance, to the point that it would take light 50 billion years to reach us. Well, that star, we can't see it. So in a natural way, we are limited by the universe itself. We can only observe the universe within a bubble with a time dimension of 13.8 billion years. Physically, it's bigger because the universe, obviously, since it's expanding, it's like you're walking on a rubber band that's stretching, right? There you go. But in terms of time, that's it.
So, as an introduction, we asked a few small questions. We can go back over them a little and see if we were more right or more wrong. Yes, thank you. So, the very first question we asked was, what is the closest star after the Sun? So here, the vast majority voted for Proxima Centauri. Here, we're pretty good.
We're good.
We're pretty good. Serious, that's the name of another star. So,
for those who know, it's in the southern hemisphere in the Centaur constellation. The brightest star is Alpha Centauri.
So we can't see it.
And Proxima Centauri. So it's called Proxima because it's the closest. We realize that between the Sun and the first star, it's still about 10,040 trillion kilometers. So it's special. It's still not obvious. So then you ask me,
Proxima Centauri, we can only see it in the southern hemisphere. Yes, we can't see it. No? All right, okay. We'll have to buy a plane ticket.
And even then, you won't see it at night, you know. It's not, you still have to, yes, it's not a very bright star. The star, all right.
The next question was, a light year, is it a distance, a duration, or a speed?
So you use the expression light year. In another context, when you say I'm 3 hours from Marseille by TGV, you know that it's a distance. 3 hours by TGV means about 800 kilometers. Because we know that the TGV travels at an average speed of about 250 with stops. So that's about it, 750 to 800 kilometers. Well, here, a light year is a distance because we know that light travels at 300,000 kilometers per second. So a light year, is the distance that light travels in 1 year. There you go. It's much simpler than saying 10 trillion kilometers. There you go. Especially since the universe is still vast enough that we immediately end up with impractical terms. And so it's better to express ourselves using that unit. We'll say that such a galaxy is 1 million light years away, which means that light took 1 million years to reach us. That's already hard enough to picture. But if we were to translate it into kilometers, then...
So the next question is, it was about how many stars are there in our galaxy? Is it a few million, a few billion, or hundreds of billions? Do we have any precise idea of the quantity?
Obviously, you can't calculate that. We don't count them one by one, you know. We make estimates, we average. Then we have a rough idea of the distance of the galaxy. We estimate there are about 200 billion stars in our galaxy. But what's new is that, I don't know if you wanted to ask this question later, it's that now we've discovered planets around stars. And today we know that each star has at least one planet, sometimes even several planets orbiting it. And so the number of planets in the Milky Way is much higher than the number of stars. So there are about 1 trillion planets just in our galaxy, at least in the Milky Way. Knowing that there are about 100 billion galaxies in the observable universe, you see the small distinction I made earlier in the bubble that we are allowed to explore, well, which has the diameter I mentioned, right? Well, there are about 1 trillion galaxies. So 1 trillion galaxies times 1 trillion planets is still a huge number. That's a lot of planets and life.
So the next question was, when we look at a galaxy that's 10 billion light years away, we see it. So 3 possibilities: as it is today, as it was a very long time ago, so going back 13 billion years, or as it will be in the future. So here, everyone basically agrees.
Yes, that's it.
We actually see the past.
Yes, you see, because actually, when you look at the sky, I invite you to look at the sky, and well, the sky gives you a false snapshot, actually. We feel like we're seeing it, like we're seeing something instantaneous and immediate, but actually no, because each light comes from a star located at different distances. And there you go, some lights correspond to a star whose light was emitted 4 years ago, others 20 years ago, others 1,000 years ago, and others 10,000 years ago. You receive all this light at once. When you return from vacation and open the mailbox, everything falls apart, especially if you've been gone for a long time. And that doesn't mean the letters were sent at the same time. And right there, in fact, you're at, how much did you say? 4 billion, 10 billion light years. So you're observing a galaxy as it was 10 billion years ago. That's not because it disappeared. That means things have happened, obviously, that we don't have access to today, but that's the galaxy as it is. And that's what allows us, by the way, to go back and retrace these stories, because, as I was saying earlier, imagine the universe as a big book. Well, the first pages are the nearby universe. And as you turn them, little by little, you go back through the distances. Well, we move forward in the story. So let's move on then.
Next question. How many confirmed exoplanets are there today that we've been able to officially detect? So,
you see, we're still just scratching the surface, right? By the way, it's worth mentioning that the first exoplanet was observed in France at the Haute-Provence Observatory, which I encourage you to visit. You can visit it quite regularly. It's open to the public at specific times, of course. And it was a pair of Swiss astronomers, Michel Mayor, and Didier Queloz, who, using a spectrograph on our large 1.93-meter telescope at the Haute-Provence Observatory, observed the first planet called 51 Pegasi. Your question,
It was, how many have we detected then?
since obviously it's the arrows, the mushroom effect, we observe, obviously we understood how to find them, and we obviously changed the programs. People started systematically searching for them, and then there's a tremendous challenge. When you find a planet outside the solar system, it's about asking and trying to answer questions we have about our own solar system. Doing science with just one object is very difficult. The solar system is unique. Are all systems the same? That's the question. So we started looking for them, and we developed many more techniques than the one used by Queloz and Mayor, who, by the way, received the Nobel Prize in 2019 for that. So there are at least 3 comparable techniques. And now we have about 5,000 to 6,000 confirmed. Okay, but that number is only provisional. We keep finding more and more. You have, for example, the Gaia mission, which is a very important mission since it is one. It was a probe, or rather a satellite, that was launched by the Europeans to observe all the stars, the billions of stars around us, nearby in detail, by measuring their movements, their positions, very, very fundamental. Well, precisely by observing the movement of a star, we think, hey, it's moving because there's something disturbing it. Well, there are also a lot of new planets being observed. So there you go. It's something that keeps going, okay?
I'm not sure if there was another question. So there was one question left, but we've already talked about it a little bit. How do we detect exoplanets? The techniques we have, well,
there are 3 important techniques. One of the techniques is to measure how the planet disturbs the star it orbits around. That's how it works. Because for a long time we thought it was impossible to detect planets around another star, simply because we realized that the star shines so much and a planet shines so little. It's as if you were out at sea trying to spot a seagull circling a lighthouse while you're 100 kilometers away from it. That sounds complicated. Oui? You agree? It's complicated, yet we manage. So, how do we manage to do it? When you've watched someone, let's say at the Olympic Games, a shot putter throwing the shot, well, as long as he hasn't released the shot, he forms a single system. The shot and him, it's kind of like the planet and the star. And so, indeed, he's the one spinning the shot, but he himself is also spinning, he's moving. So the whole system, the shot plus the shot putter, spins around an invisible point called the center of gravity of the two. There you go. And that's exactly what happens when a planet orbits a star. The star itself does this, yes, like that. So very, very little. That means it revolves around a point that's already inside the star itself. It's not somewhere else because it's very little. But today we are able to measure this movement. When the star gets closer to us, it becomes a little bit bluer. When it moves away, it becomes a little bit redder. That's an effect, a bit like if you observe when a car passes close to you, you hear the sound change. Well, that's because as it approaches or moves away, it disturbs the frequency of what's being emitted. Well, it's this technique that was used by Mayor and Queloz. So, needless to say, the technique has to be extremely precise, extremely sensitive, with the temperature maintained under certain conditions. All right, no joking, no talking, no making noise, no smoking. Well, that's it. And you keep doing it, repeat, repeat, repeat. And what's interesting also in this case is that this planet was part of a program that was meant to do something else. Mayor wanted to observe the evolution of certain stars that have disturbances, that have variations, to study the structure of stars. But they had already noticed that, maybe one day we would find a planet around a star. That was one of the possibilities, but it was really at the bottom of the list. And when they saw that, what they saw was repetitive, periodic. So when a star varies from time to time, there's a periodicity, but not as precise as that. There, it was really periodic. Yes, because it's periodic. We orbit around the Earth in 365 and a quarter days, and that doesn't change. So, from afar, if someone observes the Sun, they will see that there is a planet Earth orbiting around it. That's one technique. The other technique is more immediate. Basically, if you are well positioned in relation to the star and the planet orbiting around it, when the planet passes in front of the star, well, it blocks a small part of the star's light. So if you observe a star continuously, you'll see that at some point it's slightly less bright. And that's the first thing. But the second thing is that this phenomenon actually repeats periodically, since the planet always orbits in the same way. That's called the transit method. And this transit method applies to the solar system. You may have heard about it in 2004 when Venus passed right in front of the Sun and we were exactly positioned between them. We were perfectly aligned, you know. So we saw it for an hour. We saw the planet. We could see that black disk on the surface of the Sun. I remember I was at the Paris Observatory and we actually had the image of the Sun projected onto a screen. And we saw all of that. So there are lots of absolutely extraordinary stories about these Venus transit events, especially in the 19th century. An astronomer who had spent 18 years of his life, or 13 years of his life, trying to observe a Venus transit at Pondicherry, but unfortunately the English prevented him from boarding. He couldn't do it. He stayed 8 more years to observe the phenomenon, and then a cloud came and disrupted everything. And when he returned home, that is to the Paris Observatory, well, people thought he was dead. They had sold his apartment. In fact, his wife had found another man. That's it. So that's not easy astronomy. It's not easy astronomy in some cases. And there you go. All this to tell you that this transit technique is the second technique. Mercury can also pass in front of the Sun. We see it sometimes. It's a little bit more difficult to see because Mercury is smaller, but still, it's nice. And then a third technique is when a planet passes in front of the star. It's not necessarily associated with the star in question, but when it passes in front of the... From our point of view, in front of the star, well, it can bend the rays and create a bright flash. It's the opposite of what I said earlier. Earlier, there was less light. But here, on the contrary, you can have an effect called gravitational microlensing because every object has mass, and this mass can focus the rays and cause this lensing effect. So this too is a technique that's used less often, but it does exist. But it's mainly the first two, the motion technique and the transit technique.
Okay. Well, we've reached the end of our interview.
That's the case with serial, desirable. So we're talking a lot about Searle because of the cadmium right now, but you know, Searle is a word from Fian. Okay. Yes, because the astronomer who discovered it, Ceres, okay. Piazzi, the Italian astronomer, and he was born in Sicily, and the goddess who protected farmers was Ceres. And so he named this asteroid Ceres. And so this little planet Ceres gave its name, since it's related to agriculture, to cereal. You see how curious that is.
Very interesting. Thanks for the closing remark. So, well, don't hesitate. Normally there should be microphones going around the room if you have any questions to ask.
I have 2 questions, please. Currently, we have the telescopes that we've already included in the program, which are James Webb, Vera Rubin, and the other one. We're also going to launch Grace Roman, and we'll also have the VLT on Earth in a few years. Do all these telescopes have completely different objectives, or will there be overlaps and redundancies between the different research sites?
In general, especially nowadays, we're starting to design telescopes that are sometimes dedicated to very specific projects. That's the case with Grace Roman, for example. There you go. But at the same time, they still remain complementary. That means you always have the possibility to configure the instrument a little differently. But it's true that in the case of the ELT, for example, it's an instrument that will be 40 meters in diameter. Incredible. Can you imagine a 40-meter diameter mirror, which is a segmented mirror, right? It will have an extremely small field of view. Because the bigger the telescope, the bigger the mirror, the longer the focal length, and the more or less the field of view in the sky becomes really, really small. But obviously with precision, and first of all, a lot of power. That means you have immense sensitivity, which you don't get with a telescope with a smaller diameter. And so that means it will allow for extremely targeted observations. On the other hand, with the telescope, well, I can't remember its name thanks to you.
Grace,
The field is larger. So you'll be doing something else. You'll actually be exploring much larger portions of the sky at the same time. So you always have a compromise between precision in your aim and broader scatter shot coverage, you know. Or you look wide, you have a bit less sensitivity, but as a result, you actually have a much broader view. Or on the contrary, you will observe extremely smaller regions, but more precise and more detailed.
The current rate of expansion of the universe, I believe, comes from 3 types of measurements, each of which converges towards something that's a bit different from the others. So 3 possible estimates of the old or new kind between 67 and 67. But what do you think about it? What could it be made of? But here...
You're asking some pretty technical questions. I don't know if everyone will be able to follow. Indeed, one of the very important parameters for our understanding, our description of the world we live in, is the way, what is the rate, what we call the acceleration rate, the expansion rate of the universe. We know that every million years, obviously, space has continued to expand. So, we're in the expansion. But at what rate is it happening? Is it fast? Is it faster or slower? To find out, we measure it locally with a constant called the Hubble constant. That's it. It measures how fast. In fact, every few million years it has expanded. And there are 2 ways to get there, at least 2. One is by studying type I supernovas, which we talked about earlier. And the other is by looking at the cosmic microwave background. That is the imprint we talked about, the fossil light, the last imprint left by the universe when it was still very hot. But after that, it started to take shape. Well, these 2 values, these 2 images give conflicting results. That is to say, they are very precise, each one on its own, but with error bars, what we call error bars, which means the value is given with a certain uncertainty. And well, there is no overlap. That's always annoying. We prefer when they overlap so we can say the real value may lie somewhere between the 2. They don't overlap. So we don't know if it's... The 2 methods are different. Sometimes it's nice to have different methods, but not when we're in crises like this. So it's a tension, but there's always some... That's part of scientific work. There are always tensions like this. So whether it's the Planck instrument, it's the Planck instrument that's responsible, which gave us this beautiful image of the fossil light that we showed you earlier. Is it in the calibration, in the analysis of the Planck data, that there is actually an effect, a small effect, what we call a bias, an asymptotic shift? Or is it in the study and analysis, which is completely different, you know, from the analysis of what we call distant supernovas? Is that where the problem lies? There are other different problems there. First, you are a little more subject to the physics of these stars to know if they really are as we imagine them and so on. Okay. So on one hand, you question the astrophysics, and on the other hand, you question the instrumentation, you see. So that's why there are tensions. There are 2 communities behind the 2 projects. The communities keep passing the blame, saying, no, we're right, not you. And that's part of the healthy dialogue that can exist in the scientific field. It always helps things move forward. But there's still a bit of tension that hasn't been completely resolved. I'm having a bit of trouble.
Yes, no, it was about the first question. Anyway, you answered, Daniel. But it was actually also, regarding space telescopes, one thing we understand is that actually they are often complementary. For example, if you talked about Hubble and James Webb, there's also this aspect where actually space telescopes, when we send them, there's often a reason that's also related to what we call, wavelengths. James Webb is infrared, Hubble is, well, ultraviolet, visible ultraviolet. So what Hubble will observe will be complementary to what James Webb will observe. For example, let me give you an example. Nebulae, which are clouds of gas and dust present in galaxies. Well, with Hubble, we'll see fewer details than with James Webb, because with James Webb, the infrared also allows us to look beyond the gas clouds and better understand the environment of the nebulae. So actually, we have space telescopes. You even mentioned the VLT, Roman, and so on. Often these are tools that are complementary. When we have a telescope that is operational, efficient, and capable of observing the universe in a precise way, we don't necessarily, at least at that moment, develop a new telescope that does the same thing. So often there really is a complementarity between several telescopes, which means that in the end, we have a wide range to observe the sky at all possible wavelengths.
Yes. Also, it's worth adding that the Hubble telescope has a mirror that is 2.4 meters in diameter.
6.5 meters for James Webb.
The one on James Webb is 7.5 meters, I think. That's right.
That's better, like 6.5 meters.
6,50 m.
Hubble is located at roughly 600 kilometers in altitude, so it's in low orbit, whereas James Webb is 1,000,000 kilometers away.
To the great discomfort of,
At a Lagrange point. It's sitting comfortably in a place that's dynamically stable enough. It rotates with the Earth, it's calm, and it's always looking at the sky. The sky is opposite to the sun. For Hubble, it's more complicated. And once again, Hubble observes from the ultraviolet up to the edge of the visible spectrum, while James Webb takes over. So every time we open a different window to the world and observe, discoveries are almost guaranteed. Well, we don't know what those discoveries will be. We can guess some of them, but we have to discover. We have to observe new things. It's automatic. And it's very important to change your perspective. You know, if you look at the world around you with red glasses, you'll only see red. If you look with green glasses, you won't see any red. So it's important to have a combination of all that.
Anyway, feel free to follow us on YouTube. We'll be able to put the replay up and plenty of other replays on the YouTube channel. And we'll be able to hold more conferences on other topics as well. So feel free to stay tuned. There you go. Thank you very much anyway.